So let's, before we look at the solution, look at calculation of the flow rate. So let's start again like we did with the boundary conditions with the exact expression. So I know that Q by 2, because of the symmetry of the problem, will be equal to the integral of 0 to h of x, right, the wavy wall, times the non-dimensional u dy. So of course, if I replace the dimensions of all things, I'll get the dimensional version of Q. Let's for the moment call this integral 0 to h u dy as I, which depends on epsilon, because the top limit depends on epsilon, but also u depends on epsilon indirectly through the boundary, right? So the solution we obtain will certainly depend on epsilon as well. Okay, so the idea now is, I know that well, basically this is the exact expression, but the actual solutions I'm going to obtain, I'm only going to have them from 0 to plus half, which is the value of h of x comma epsilon at epsilon going to 0. So what we really would like to do is Taylor expand this integral itself about epsilon equal to 0, and then each term in the Taylor series that we obtain will be an integral defined from 0 to half, because h of x comma epsilon where epsilon is 0 is just half. So let's Taylor expand the integral I of epsilon, which is basically q by 2. But we need to be careful now that when we apply the Taylor series, we'll have to take derivatives with respect to epsilon. But to do that, we'd have to use the Leibniz rule. Which is what allows us to take a derivative from outside the integral into the integral, because ultimately we will want to take derivatives of u with respect to epsilon and then use our power series solution. Okay, so let's take it step by step. Right, so what I would have here is q by 2 as a Taylor series is basically I of 0, where I substitute 0 right here, plus epsilon di by d epsilon plus epsilon square by 2 d square I by d epsilon square. Alright, so now let's look at what di by d epsilon is. So before that, it's obvious immediately that I of epsilon is just integral 0 to half. Now u when epsilon is 0, if you look at our power series solution, is just u naught. So this is just the flow rate through flat plates if epsilon was 0. So that's what we'd expect to be the first term in the approximation. But now di by d epsilon, of course I forgot to say, evaluated at epsilon equal to 0. But to do that, we first have to calculate di by d epsilon and only then substitute epsilon equal to 0. So let's see what di by d epsilon is in general. So this is d by d epsilon of the integral 0 to h of epsilon, where I suppress the dependency on x, times u, and I would like to take d by d epsilon into the integral. So because then du d epsilon is just u1 plus epsilon u2, and when I put epsilon equal to 0, it is just u1. Right, that's how a Taylor series works. But I need to take the derivative inside, and so that's where I use Leibniz rule. Right, which basically says that this term must be equal to du by d epsilon dy plus, now remember, it should be the integrand evaluated at the upper limit times the derivative of the upper limit with respect to epsilon minus the same at the bottom if the bottom was dependent on epsilon, but it is not, so you have no other contributions. So these are the two terms. So we have an extra term coming out here because the upper limit basically depends on epsilon. And now if I choose to evaluate this at epsilon equals to 0, what I will obtain is simply integral 0. Now h at epsilon equal to 0 is just half. Du by d epsilon at epsilon equal to 0 will just be u1. So it's the first order, it's the integral from 0 to half of the first order correction to the domain field u, but I have a correction coming from the walls. And that will be, now this can be expanded as a power series, but so can this term. So what I will get is just, but first let's write this out. dh by d epsilon, remember, is just sine 2 pi x by 2. Right, let's go back to the expression for h. Right, so this is h of x. So d by d epsilon is just sine 2x by 2, and you have no higher order derivatives. And now u of h, if you had again taken a power series expansion here, is u naught plus epsilon u1 and so on. But when epsilon is 0, you will just get u naught evaluated at, again, oh yes, so here we should be careful, I'm sorry. So we can't directly substitute that. U of h again is not known to us, so we need to replace u of h by its domain perturbation form, which is itself written as u at half, right, plus epsilon sine 2 pi x by 2 dou u dou y at half. Right, so now we can take it. So you have sine 2 pi x by 2 coming out of here, and then this term, when I expand and I put epsilon equal to 0, I'll get rid of that term. And then u at half is again the full actual power series evaluated at half. Right, but when I put epsilon to 0, I just get u naught. So the only surviving term here is going to ultimately be u naught at half. So this is my first, the first expansion in the term. Similarly, now I can write out the higher ordered expansions. So let's go to second order here. This term, you'll see now, if I just have to repeat the Leibniz rule on this expression here for d by d epsilon. So the first term will just give me the integrand now evaluated at h plus, so that all comes from the first term. I then take the derivative of the second by using the product rule, u of h by d epsilon. Right, so it's whatever I get here, that stuff take it is derivative with epsilon. Times dh by d epsilon plus now u of h times dou square h by dou epsilon square, but I know that this is 0 because h has no second order dependence on epsilon in the way we have written it. Alright, so now it comes, so we obtain the expression here. I can do the same for these two terms as well. So you'll see now that if I evaluated this at epsilon equals 0. The first term will just be 0 to half. Now u2 is the only term that will survive the Taylor series after putting epsilon going to 0. After you substitute the power series here, take the second derivative, set epsilon to 0, you only get u2. Plus now, I take this derivative du by d epsilon, evaluate at h and then put epsilon equal to 0. All I'm going to get is u1 right, so I'm going to get u1 evaluated at h but that in turn can be written in a Taylor series expansion as follows. So I would have u1 evaluated at h as u1 evaluated at half plus d dy of epsilon and so on, but the epsilon terms would go to 0. Right, so I just have u1 evaluated at half, right, times again dh d epsilon, which will just give me a sine 2 pi x by 2 contribution. Right, so I hope you can work this out in more carefully if you wish, but the idea is you first, we only know u as a power series expansion, so you take the derivative with respect to epsilon, you will get u1 plus epsilon u2 and so on. If you evaluate all of that at h and then set epsilon to 0, all the higher order terms will go, you'll just have u1 at h, but u1 at h itself can be expanded using domain perturbations, but when you expand and put epsilon to 0, you just get the leading contribution. So once again, conveniently, you see that the term we are interested in is all the terms get evaluated in the domain of the problem that we are solving, that is the domain from 0 to half, and the boundary values of the power series functions at the boundary half, the kind of fictional boundary half, which is what we want. So that is this term, and then I get another contribution from here, which normally looks the same but is slightly different. What this is, you go to u at h, you expand that out as we have done here, you take the derivative with respect to epsilon, which will leave only this term surviving, right, sine 2 pi x by 2 by 2 comes from here. The epsilon of course goes off when you take the derivative to epsilon, and then I have du by dy, right, evaluated at half, which will certainly survive. Evaluated at half, but again if I put the power series expansion here, I have actually dou u naught by dou y, dou u 1 by dou y and so on, but when I put epsilon to 0, it's just dou u naught by dou y. Right, so I have that term times dou h by dou epsilon, which will throw out another sine 2 pi x by 2, so that this term is multiplied by the whole squared. So there you have it. I have now two second order obtained expressions that I was after. One is here and the other one of course is right here. And so now I can substitute these expansions into my original expression. So I'll have q by 2 is actually just the integral of the flat channel solution from 0 to half, plus epsilon times the integral of the first order perturbation correction, again from 0 to half, plus a correction coming from the domain involving u naught at the fictional boundary half. And then at the next order I'll have plus epsilon squared, the integral of u2, and then two more correction terms, one involving u1 and the other involving a derivative of u naught, both evaluated at half. So you see that the important thing to note here of course is that the flow rate is not given by its naive expansion. So by that I mean, if let's say you get the solution of the problem using domain perturbation. You now know that this solution is only available from 0 to half. And then you might think, okay, the flow rate through this solution is just an integral of the power series solution, that is integral of u0 plus epsilon u1 plus epsilon u1 square from 0 to half. But that would be wrong, because that is only part of the flow rate. It only accounts for these terms here, the first integral terms. You will be missing out the contributions from these boundary terms that that can only be accounted for correctly if you use the Leibniz rule, which respects the fact that the limits of integration themselves are changing with epsilon. So it's important whenever you calculate integral quantities while using the domain perturbation method to derive the Taylor series expansion for those integral quantities using the Leibniz rule. Only then will you get these additional terms. If you simply apply the integral in a naive form to the problem about the so-called base domain, which is the domain when epsilon is 0, then you will not get the correct result. However, now in our problem, it will turn out that all these boundary contributions are going to go to 0. You can see that in two ways. One, you can look at what the values of u0 at half and u1 at half and so on are actually given by. So they are going to be given by basically the perturbed form of a boundary conditions. So for example, if we substitute the power series here and look at their various orders, at 0th order, the only term that survives in this boundary condition is u at y equal to half, but after putting the power series expansion, you will get u0. So u0 at y equal to half is actually equal to 0. That comes from the 0th order version of the problem. At first order, similarly, after substituting here, you will get dou u0 by dou y times sine 2 pi x plus u1. So u1 is actually minus dou u0 by dou y sine 2 pi x at half. And if you come here, you will see that that will cause these two terms to cancel out. So you say take sine 2 pi x common, you'll have u1 plus dou u0 by dou y sine 2 pi x by 2 at y equal to half, but they will cancel out from the boundary condition on u1, from the domain perturbation boundary condition. So these two terms actually cancel off, and this term is identically equal to 0 if we were to apply the boundary conditions we obtained from the domain perturbation at each order. However, you could have anticipated this even earlier. So if we had looked at the general form here before we looked at applying epsilon going to 0, we'll see that we have u at the wavy wall h, but I know that this itself must be equal to 0 exactly. So right at this stage itself, I could have set this term to 0, in which case after applying a successive derivative and Leibniz rule, even the derivatives at h will be 0, and taking epsilon to 0 will just give me the integrand terms. So either way, either by recognizing it right here or by looking at the boundary conditions, the final result for q by 2, right, which can be calculated from our domain perturbation solution, looks as follows. And this you see is actually turns out in this problem to be just the naive integral that one would take if you weren't careful about applying the Leibniz rule and treating the expansion in epsilon. So as a rule of thumb, you can write down the flow rate to any other integral quantity in terms of this naive expansion on the base domain, which is basically the domain in the limit epsilon going to 0. Provided your fields satisfy no slip or 0 boundary conditions on the wavy walls or on the complex shaped walls. But in general, if your velocity, let's say, was non-zero at the wall, right, it satisfied some sort of, let's say, electroosmotic flow condition on the wavy wall, then you would get contributions from these terms which would be non-zero. And then trying to calculate the flow rate with this naive integral would be wrong because you will have extra terms. So it is important to remember that in the domain perturbation problem, one aspect is to Taylor expand boundary conditions using Taylor series and the idea of analytic continuation. But the other subtlety is whenever you're calculating integrals across the domain, you need to be careful to express those integrals as Taylor series using Leibniz Rule in order to get the correct result from the solution of the domain perturbation problem for those integrals. Alright, so the effort we put in here is not only to stress on this important point regarding integrals in the domain perturbation method, but now this also gives us a convenient condition on our problem that we can use instead of one of the boundary conditions to aid in the solution of our problem and to aid in the calculation of the flow rate. That is the following. So intuitively, one could imagine that in this Wavy-Wall channel, regardless of the waviness, under steady state conditions, even though locally the u velocity field will vary, so u will be slower here, it will accelerate in the narrow portion, decelerate, and so on. You would expect that the total flow rate in the channel is constant. Indeed, the reason the fluid accelerates into the narrow part and decelerates into the larger part is because the flow rate remains constant in the channel. This is true of flow under steady conditions. So this would mean that dq dx, or the derivative of q along the x direction must be 0. But instead of just appealing to your intuition, we can prove this exactly from the equation of continuity. Because in fact, the result that the flow rate remains constant along x is a consequence of the fact that you have mass conservation, along with the fact that there is no fluid entering or leaving from the boundaries. So if I write down the continuity equation here, du dx is minus dv dy in general now, not for the perturb problem but for the full problem. And I know again for the full problem that q is just integral of u. Let's say q by 2 is integral of u 0 to h. Then I can say that half dq dx is just dx of integral 0 to h u dy. Right, but now again I can use the Leibniz rule. So this is integral 0 to h du dx, or dou u dou x rather, partial derivative, dy plus dh dx, whose form we know, but more importantly u evaluated at h. From no slip this is 0. So again this term has no contribution. But now I can replace the integrand from using the continuity equation by minus dou v dou y dy, which is just v at 0 minus v at h, both of which are 0. And so I get the result finally, as we expected intuitively, that dq dx must be equal to 0. Now I can prove this not only for the full problem, but if you want, you can, instead of applying this to the full problem, you can Taylor expand this expression. So you can start with the general form of apply Leibniz rule and start with the expanded form of the integral, and then use the continuity equation as well, and you will get the same result. Just as I showed you here, that you can either use the no-slip condition in its exact form right at the beginning, or even if you don't use it there and do the perturbation expansions, you will use the perturbation expansions to get the expression and ultimately use the domain perturbation boundary condition, you will get the same result. That's just a check on consistency, because after all the domain perturbation boundary conditions have been derived respecting the power series expansion and as well as the Taylor series boundary condition. Okay, so this is an important result. Let me now mark it down for future reference. Right, so I had the domain conditions of interest all as equations 1, A, B, C. I have the boundary conditions here. Let me call this no-slip boundary condition at the top wall to A, the symmetry condition at the center to B. This equation, which is the domain perturbation form of the boundary condition, let me call it 3A, and there's a corresponding 3B which I have not written down, but for the D component of velocity. which is identical to this except we replace u equal to v. And then I can look at I write down the perturbation expansions, the perturbation expansion. As 4, and then finally this relationship for the flow rate as 5a, let's say, and this important result as 5b. And you will see how we can use this result basically as it cannot replace anything, because so it's not an additional boundary, it's not an additional condition, right? Because we have seen that our problem is already fully specified. We had exactly the number of boundary conditions we need to fully determine our solution. So this cannot be a new condition, and we know it is not a new condition because after all, to obtain this result we have used our boundary conditions twice, right? We use the boundary condition on u, we also use the boundary conditions on v. So this is just another form really of the no slip and symmetry conditions we already have. So at best it will just, it's like a different way of implementing the boundary conditions, and in our problem we will see that it will save us some amount of algebraic work. And recognizing such things not only helps us better understand the problem, so here we are made aware of the fact that the flow rate must be constant along the channel, but also helps in the solution procedure. So it's always very useful before directly diving into calculate the fields by either doing the analytical solutions or numerical computations, to spend some time working with the equations to see how you can re-represent them. And that helps us often identify the best way to obtain solutions both numerically or analytically by deciding which form of the boundary condition to impose. Ultimately, you will get the same results. It's just a matter of calculation efficiency and also as a way to check the problem. So for example, if I obtain the solutions using the boundary conditions in their native form, or even computationally, let's say, I can then come back and make sure that I've got the correct solution by checking that the derivative of the solution of the flow rate that I obtain after using the integral formula 5a, if I calculate the flow rate using 5a, I can check whether its derivative with respect to x is indeed 0, or in other words that the flow rate is indeed constant in the x direction. Or I can apply 5b instead of one of the boundary conditions and later use that boundary condition as a way to check on errors, either. Okay, so let's now set all of this aside as we have set up our problem nicely, and now begin our task of actually solving for the velocity fields perturbatively in the way that we have done previously, except now that we should remember epsilon is now in the boundary condition rather than in the domain equation, but the procedure will work the same as before, as in the earlier lectures. So we will solve for the velocity fields at first order and so on to second order, and from there one of the things we are interested in is not only the fields but also calculating the flow rate, because we would like to know how the waviness affects the flow rate. Is the flow rate going to increase or decrease, and what is the dependence of that increase or decrease on the aspect ratio of the waviness. So if we have a rough surface versus a structured surface, which one has a stronger effect on the flow rate. Now, before we do that, one more thing. It's interesting to ask whether we expect the flow rate to change at first order, that is at order epsilon, or only at second order epsilon squared. So one way to do this, of course, is to do the calculation and check, but it's useful beforehand because one might want to know to what order do I have to go to get the first correction to the flow rate. So in this case, we can tell right at the beginning that the flow rate will not change at order epsilon even without doing any calculations. Why? Purely from a symmetry argument. So if we go back to how epsilon was introduced into the problem, you see epsilon was introduced to the boundary condition, right? That y is half plus epsilon sine 2 pi x. So if the flow rate was to have a correction that is proportional to epsilon, it would mean that if epsilon is positive, that correction would be positive. If epsilon is negative, the flow rate correction would be negative, or the flow rate would decrease or increase depending on the sign of epsilon. But if you see the form of the boundary condition, that would be aphysical, right? Because the modulation is sine 2 pi x. If I make epsilon minus 1, that's equivalent to doing a phase shift of the boundary condition by 180 degrees or by pi. Right? Because sine minus 2 pi by x is minus sine x. So if epsilon has a negative value instead of a positive, it's just like saying the waviness of the wall is exactly the same, but it's just phase shifted. And in a physical problem, there is no real origin for x to define a phase shift, right? It's the origin of x is arbitrary. Therefore, the phase of this sinusoidal variation is also arbitrary. Only its frequency should matter. So therefore, the flow rate, an integral quantity like the flow rate, should not depend on the sign of epsilon. The velocity field can certainly depend on epsilon, right? Because if I phase shift or just shift the boundary conditions relative to the arbitrary origin, the fields will also go along with them. But the flow rate, which is a quantity which is integrated over the domain and which should not depend on the origin of the problem, right, should certainly not show any sign dependence on epsilon. Therefore, I can already say that the flow rate will only show me a correction at order epsilon squared. Now, this is not because of some deep physics of the problem that says that it is like a very small effect that is coming on epsilon squared. It's merely a consequence of the way I have represented the perturbation to the wall by using epsilon as the way I have perturbed that boundary condition. If I had used epsilon squared here, then it would come, at that order, but it would still be order epsilon squared. So it doesn't really change that fact. But what I want to highlight now is that already we can tell before calculating that we need to go to second order to get the correction to the flow rate, which is why throughout I have already expanded to second order. So although I would have preferred to shorten my lecture and just stop at first order and ask you to do the hard work of going to second order, in this problem that's not an option, because if I want to calculate the change to the flow rate, I know beforehand that I have to go to order epsilon squared at the very least. So we can brace ourselves for a long calculation here. But we will see that as we understand the structure of the calculation, the problem will help us going to calculate that correction to the flow rate, and we could save some time as we go along. But let's not worry about that right now. Let's tackle the problem stage by stage, starting with the zeroth order, which is the simplest. It's always nice in perturbation problems that the first stage is very simple, backed by construction, of course. And then take the first order and then so on step by step.